Have you ever wondered how quantum computers work and how they differ from classical computers? Welcome, my curious friends, to the enigmatic realm of quantum computing. Imagine a world where a coin isn't just heads or tails but both at the same time. That's the realm of quantum physics, and it's the foundation of quantum computing. Unlike classical computers, which use bits as their smallest units of information, quantum computers use quantum bits, or qubits. These qubits can exist in multiple states at once, thanks to a characteristic called superposition. Furthermore, they can be entangled, a phenomenon where the state of one qubit directly affects the state of another, no matter the distance. These unique characteristics of superposition and entanglement make quantum computers fundamentally different, and potentially far more powerful than their classical counterparts. So, buckle up, as we delve deeper, prepare to have your mind blown by the fascinating world of quantum mechanics. Quantum mechanics may sound intimidating, but fear not, we're about to break it down. Picture this. You're at a crossroads, and you can take either the left or the right path. In the classical world, you'd choose one. But in the quantum world, you can take both paths simultaneously. This is the principle of superposition. A quantum bit or qubit, unlike a classical bit, can be in a state of 0 or 1 or both at the same time. It's like having your cake and eating it too. Now imagine you have two particles. In the classical world, these particles would behave independently of each other. However, in the quantum realm, these particles can become entangled. This means the state of one particle is directly related to the state of the other, no matter the distance between them. This spooky action at a distance, as Einstein called it, is known as entanglement. It's like having two magic coins that always land on the same side, even if they are flipped on opposite ends of the universe. Finally, let's talk about quantum tunneling. If you throw a ball at a wall in the classical world, it would either bounce back or break through, depending on the force you used. In the quantum world, however, the ball can tunnel through the wall with no apparent breach. It's as if the ball has ghosted through the wall. This principle allows quantum particles to move through barriers that would be insurmountable in the classical world. So there you have it, the principles of superposition, entanglement, and quantum tunneling. These are the building blocks of quantum mechanics, the strange and fascinating rules that govern the microscopic world. It's a bit like learning a new language, isn't it? But once you start to grasp these concepts, you'll begin to see the world in a whole new light. Now that we have a basic understanding of quantum mechanics, let's move on to how these principles are applied in computing. Quantum computing, a field that's as fascinating as it is complex, but what does it actually mean? Well, to understand quantum computing, we first need to dive into the world of qubits. Unlike classical computers, which use bits that can be either 0 or 1, quantum computers use quantum bits or qubits. A qubit can be both 0 and 1 at the same time thanks to a quantum peculiarity known as superposition. Picture it as if you're in a room with two doors. In the classical world, you'd have to choose one, but in the quantum world, you can walk through both doors simultaneously. That's superposition. Now let's talk about quantum gates. In classical computing, we have logic gates that perform operations on bits. Quantum gates, however, manipulate qubits. They transform the state of qubits in various ways, allowing for a vast array of potential outcomes. This is where another quantum property called entanglement comes into play. When qubits become entangled, the state of one qubit becomes connected to the state of another, no matter how far apart they are, so a change in one instantly affects the other. It's like having two magic dice that, no matter how far apart, always land on matching numbers. Lastly, we have quantum circuits. These are sequences of quantum gates, similar to how classical circuits are sequences of logic gates. The difference is, quantum circuits can perform complex calculations in fewer steps than classical circuits. This is because they can process a vast number of possibilities all at once, rather than one by one. It's like trying to find a needle in a haystack. A classical computer would check each piece of hay one by one, while a quantum computer could check them all simultaneously. With these new concepts, we're ready to explore some of the most groundbreaking quantum algorithms. Imagine being able to factor large numbers in a snap. Shor's algorithm makes this possible. This quantum algorithm, developed by mathematician Peter Shor, is a game-changer in the realm of number theory. It's a prime example of how quantum computing can outperform classical algorithms. So what's the magic behind Shor's algorithm? Well, it's all about leveraging the unique properties of quantum mechanics. The algorithm uses quantum bits or qubits, which can exist in multiple states at once, thanks to a phenomenon known as superposition. This means that a quantum computer can process a vast number of computations simultaneously, making it exponentially faster than a classical computer when it comes to factoring large numbers. But the real genius of Shor's algorithm lies in its use of another quantum property: entanglement. This is where the state of one qubit is intrinsically linked to the state of another, no matter the distance between them. Shor's algorithm uses this property to effectively entangle the factors of a number, allowing them to be determined simultaneously. So what does this mean for us? The implications of Shor's algorithm are profound. In the world of cryptography, for instance, many security systems rely on the difficulty of factoring large numbers. If a quantum computer running Shor's algorithm could crack these codes in a fraction of the time it takes a classical computer, it would revolutionize the field. But it's not all about breaking codes. The ability to quickly factor large numbers has potential applications in many areas of science and technology. It could accelerate the development of new materials, aid in the modeling of complex systems, and even help us understand the mysteries of the universe. Impressive, isn't it? But there's more. Next, we're going to talk about another revolutionary quantum algorithm. Searching a database might seem mundane, but Grover's algorithm takes it to a whole new level. The world of quantum computing is full of surprises. And one of them is Grover's algorithm, a unique approach to database search. Unlike classical algorithms that must sift through each item in a database one by one, Grover's algorithm can find the needle in the haystack in far fewer steps. Here's how it works. Grover's algorithm manipulates quantum states to create a superposition of all possible answers. It then uses a process known as amplitude amplification to increase the probability of finding the right answer. It's like having a magical magnifying glass that zeroes in on the correct data. But what does this mean in practical terms? Imagine a phone book with 1,000,000 names. A classical computer would, on average, need to look through 500,000 names to find the one you're after. But with Grover's algorithm, it would only need about 1,000 steps. That's a massive leap in efficiency. This isn't just about speed though. The real magic of Grover's algorithm lies in its potential applications. It could revolutionize areas where search is critical, like artificial intelligence, machine learning, and cryptography. It could make our virtual assistants smarter, our online security tighter, and our scientific research more profound. Of course, it's important to remember that quantum computing is still in its infancy. We're still figuring out how to build reliable quantum computers, and there are significant challenges to overcome. But the potential is undeniable. With Grover's algorithm, we're not just searching faster, we're searching smarter. And it's not just Grover's algorithm. There are other quantum algorithms out there, like Shor's algorithm for factoring large numbers, that could also outperform classical algorithms. Each one offers a unique glimpse into the future of computing, a future where we harness the strange and wonderful rules of quantum mechanics to solve problems that today's computers can't even touch. These quantum algorithms open up a world of possibilities, don't they? Quantum computing is not just a concept, it's the future. As we dive into the final phase of our quantum journey, we'll explore the future implications of this innovative technology. The current state of quantum computing is like watching a child prodigy grow. It's still in its infancy but shows tremendous potential. Many tech giants, including Google and IBM, are investing heavily in quantum research. They're not just playing with qubits for fun, they're betting on a future where quantum computers will solve problems that are currently beyond our reach. Imagine a world where we can model complex biological systems at the quantum level. This could lead to breakthroughs in the creation of new drugs and the understanding of diseases. Or consider the field of cryptography, where quantum computers could crack codes that would take classical computers centuries to decipher. But it's not all roses and rainbows. Quantum computing faces significant challenges. The quantum state is notoriously fragile, easily disturbed by environmental factors. This makes building and maintaining a stable quantum computer a Herculean task. Moreover, quantum algorithms are complex, requiring a deep understanding of quantum mechanics to develop. There's also the ethical quandary. What happens when quantum computers fall into the wrong hands? Could they be used to undermine security systems, leading to a new era of cybercrime? These are questions we must grapple with as we navigate the quantum future. Yet, despite these challenges, the quantum race is on. The potential benefits far outweigh the hurdles. We're on the brink of a quantum revolution that could redefine our understanding of the universe and our place within it. As we move forward, we must remember that quantum computing isn't just about faster processing speeds or bigger data sets, it's about reimagining what's possible. It's about pushing the boundaries of human knowledge and capability. Quantum computing has the potential to revolutionize our world, so keep an eye on this fascinating field. It's not a matter of if, but when, quantum computing will transform our reality. Buckle up, folks, we're in for one heck of a quantum ride. So, that's a quick dive into the fascinating world of quantum computing. We've journeyed from the fundamental principles of quantum mechanics to the compelling realm of quantum computing, and finally, the game-changing potential of quantum algorithms. Quantum mechanics, with its principles of superposition and entanglement, has shattered our classical understanding of the universe. It's a realm where particles can exist in multiple states simultaneously, and where particles separated by vast distances can still influence each other instantaneously. From this mind-bending foundation, we've seen the emergence of quantum computing, a technology that leverages these quantum principles to perform calculations in ways that classical computers simply cannot. Quantum bits or qubits, unlike their classical counterparts, can exist in a superposition of states, allowing for the simultaneous processing of vast amounts of information. We examine the power of quantum algorithms, particularly Shor's and Grover's algorithms. Shor's algorithm, with its ability to factor large numbers exponentially faster than any classical algorithm, could revolutionize cryptography. Meanwhile, Grover's algorithm, with its promise of significantly speeding up database searches, could transform data processing and analytics. These quantum algorithms, and many more yet to be discovered, have the potential to outperform classical algorithms in ways that were previously unimaginable. They exemplify the promise and potential of quantum computing, an exciting field that is still in its infancy. But remember, understanding quantum computing isn't just about mastering complex theories and algorithms. It's about embracing a new way of thinking, a new way of seeing the world. It's about stepping into the quantum realm and exploring the incredible possibilities it holds. So, let's keep learning, keep exploring, and keep pushing the boundaries of what's possible. Because at the end of the day, we are not just passive observers in this quantum universe, we are active participants. And it's up to us to shape and define the future of quantum computing. Remember, the future is quantum, and it's already here. Thanks for joining us on this journey into the quantum realm. If you enjoyed this journey into the quantum realm, don't forget to like, share, and subscribe for more fascinating content. But don't stop there. Join the quantum revolution. Dive deeper into quantum mechanics, explore the intricacies of quantum algorithms, and follow the latest developments in quantum computing. Remember, every like, share, and subscribe helps us bring you more in-depth explorations into the world of quantum, and the more we learn, the more we can push the boundaries of what's possible. So, let's keep learning, keep exploring, and keep pushing the boundaries of the quantum universe. Because at the end of the day, it's not just about understanding the quantum world, it's about shaping its future. So let's shape that future together. Thank you for your support, and remember, the future is quantum, and it's already here.